So on this good note, let's start again. And so this is once again a letter that was sent by Pablo Picasso at the beginning of the 20th century. And although the writing is a little difficult to read, you can probably make out that it was sent to Paris, to the 10 Rue d'Anjou, and to Monsieur Jean Cocteau. And when this letter was sent at the beginning of the 20th century, so in 1919, only humans with our biological neural networks could read this writing. But in the second half of the century, there were algorithms that were invented that could also decrypt this writing, and specifically artificial neural networks. And nowadays, we have these kinds of complicated networks that are made of thousands of neurons like these. And these networks or algorithms can take very noisy input and translate it into an exact value with close to perfect accuracy. Now, the problem with these algorithms is that they work well only in constrained environments, meaning that they work well only when their input can take a few distinct values or a few distinct classes like these different letters. And even with these few classes, they require thousands of neurons to work efficiently. And this is a problem in the real world environment because our world is not made of just a few classes, but is made of many different classes, and indeed of infinitely many classes. Yet, our brain and our algorithms are made of a finite number of neurons. And so this is the question I'm working on. How can you address or deal with infinitely many classes with a finite number of neurons? And specifically, I'm interested in how we can improve our algorithms by understanding how the brain does things. So let's look at how the brain does it. And let me introduce this example of the 4 Mandarin tones. So Mandarin is a language that has these 4 tones, or 4 changes in pitch, and all these tones bear a meaning. And you should think of these tones as classes, right? Because Mandarin speakers have to distinguish between these tones, just as we have to distinguish between these classes or these letters. And it turns out that as non-Mandarin speakers, we're pretty bad at this task. So with 75% accuracy, this leaves us about 25% chances of mistaking our mother for a horse. But there's hope because we can improve on this task and reach around 90% correct accuracy. And now what's interesting is to look at what goes on in the cortex as we learn. So what you're looking at here is a horizontal cross-section through the brain. And in yellow are neurons that are activated when the subject hears tones. And what you should notice is that before training, there are fewer neurons that are activated as after training. And so what you should get from this is the following. First, that neurons are a limited resource. And because of this, the brain assigns relatively few neurons to classes that are irrelevant to us. But if these classes become relevant, then the brain can reassign neurons to this class, and this leads to an increase in performance. So now the next step is was to include this process into an artificial neural network. Jeez. All right. Whoa. So yeah, so I'm working with this type of network made of 20 neurons, and this is the type of input that I'm using, so handwritten digits. And this is a depiction of... All right, no, yeah. Without delay, yeah, so we're looking at here, I think the pointer. All right, so you can imagine where I'm pointing. So now I'm pointing at the neurons, all right? And so what you see here are 20 neurons, and within each is the favorite class of each of these neurons, which means that, no, it's the, all right, anyway. So we're, I'm trying. All right, so what you're looking at here are these 20 neurons, and so in yellow are the neurons that will be activated if the network sees a 1, right? So if now you see a 5, the network is presented a 5, then this one neuron will become activated. And this is equivalent to what you observe in the brain, where you have certain neurons that are activated by a certain tone. And what we know from biology is that training increases the number of neurons that are responsive to a certain class. And so now the question is, can I reproduce this in my network? And so by looking at the publication that described this mechanism in biology, I came up with a simple mechanism that could explain this process. And by including this mechanism to my network, I was able to reproduce this mechanism. So here what you should notice here, so that there is an increase in the number of neurons that are responsive to the 5, right? So when I present a 5, more neurons are activated, and this is equivalent to what you observe in biology. More neurons are activated by the tone. And finally, and importantly, by this increase in neurons led to an increase in the performance of the network. And so this is equivalent to what we observe in biology, right? Or what we observe in humans. As we improve our performance in classifying the tones, this network also improves its performance at classifying 5s by having more neurons dedicated to 5s. Yeah, so, and I'm just going to conclude. So, so this means that in real life, if a neural network is provided with the mechanism that developed, it can reassign its neurons to the classes that are relevant to it, and whether these be trees, or traffic signals, or letters written by Picasso. And thank you.